Okay, so in example 2 it says the number of bacteria in a petri dish doubles every 3 hours. So what that means is every 3 hours it's going to double in quantity. And in part A it says if the initial population is 36, so we're starting with 36 bacteria, complete the table below to determine the population after 12 hours. Now if it's growing by a factor of 2, so it's doubling every 3 hours, then I can sit there and multiply by 2 every single time, which is essentially what I'm going to do to actually figure out how many bacteria there will be in 12 hours. That's the method I'm going to use right now. Eventually, we're going to look at writing a formula so that I don't have to sit there and keep multiplying by 2 every single time. Especially if the question asks me what the bacteria population would have been after a day or even after 1 week. There's way too many hours for me to sit there and do doubling and doubling and doubling over and over again. So eventually we're going to look at how to write a formula for this instead of just sitting there and multiplying by 2 each time. So let's take a look at the table. The first thing you should notice is that in the table, the hour values go up by 3s. Why do you think I did that? Well, I don't really know what happens after 1 hour or after 2 hours, but I do know what happens after 3 hours exactly. And I know that the population is actually going to double every 3 hours. So the whole idea here for setting up the table in this form is because I know what's happening every 3 hours. So I made sure that my time values went up in 3-hour intervals. So my initial population, going back to the question, was 36. And so in 3 hours, I know that this quantity is going to double. So I'm going to take this quantity and I'm going to multiply it by 2. And in 3 hours again, it's going to double again. So I'm going to have 36 times 2 and then times 2 again, which I'm going to simplify and write as 2 squared. Okay, so 2 times 2 is the same thing as 2 squared. And the reason why I'm doing that is because I know there's going to be a pattern that comes up and I want you to see if you can develop the pattern. Okay, the next one. In another 3 hours, the population is going to double again. So it's going to be 36 multiplied by 2 times 2 and then times 2 again. So that'll give me 2 to the exponent 3. And then in 12 hours, I'm going to have 36 times 2 times 2 times 2 times 2, which is 2 to the exponent 4. And I'll actually evaluate this one because this is the one that I'm actually looking for the value of. And if I use my calculator, I get 36 times 2 to the exponent 4 is 576. Perfect. So what that means is, therefore, the population of bacteria in 12 hours is 576. Okay? So let's just make sure this makes sense. So if I started off with 36 bacteria and I double that after 3 hours, I would have 72. Okay, that makes sense. And if I double it again, I get 144. I double it again, I get 288. And if I double it again, I get 576, which is exactly what I got in the chart as well. What you'll notice is that I can actually probably write an equation for this function instead. And what I can use is the same idea that we had in question number 1. And I can probably write the population as my initial population of 36 times the growth ratio, because it is a growing problem. You'll notice that the growth ratio, or the quantity that I need to multiply by each time, is 2. So my growth ratio in this case is actually 2. And the exponent part here is the one that's going to be a little bit different. We're going to come back to the exponent part that would normally go here in 1 second. Okay? Part B says, how many growth periods are there in 12 hours? So growth periods means the number of times that you've had to multiply by 2. And I know that in 12 hours, we only multiplied every 3 hours. So that gives me 4 growth periods. And that makes sense with the table that I have here. I multiplied by 2, 1, 2, 3, 4 different times to figure out how many bacteria I would have at the end of 12 hours. So this is kind of weird because I know to find the answer here, notice that the 36 is the same here and the 2 is the same here, but the exponent here I had is 4. Now the weird part is I knew that it was 12 hours. Why would the exponent be 4 when I'm looking at a time span of 12 hours? Well, the reason for that is because I actually had to take the time I was looking at and divide it by the amount of time it takes for it to actually double. So T represents the amount of time you're looking at, and D represents the doubling time. Okay, that's how much time it took to double. So if I actually rewrite my exponent part here, and instead of just writing x, for example, or T in this case, I can write T over D, and this would be my equation for the population growth of the bacteria. And I can re-simplify this, and I can actually change the denominator part here to a base of 3. And that makes sense because this exponent represents that every 3 hours, the population is going to actually double. Now, if I plug in a time value of 12 like I had here, so the population after 12 hours would be equal to 36 times 2 to the exponent 12 over 3. And I know that 12 over 3 reduces to 4. And lo and behold, you'll see that looks exactly like the question that we had earlier in the table. And that's 576 bacteria. So we're going to look at how to write different equations when the amount of time it takes for something to double or triple or whatever the problem may be is not just a single amount, like an hour or a year. Instead, it's over several hours or several years.